Welcome to the 9th preview video for Math S-322. This covers 3 topics that my freshmen at Harvard are generally rather shaky with, in spite of the fact that all 3 of these are very important. First of them is inverse functions, how you differentiate things like the arcsine function and arctan function. My experience is that students know the differentiation rules, but almost none of them know how to prove them correctly. Second topic is L'Hopital's rule, which students love to apply. Here we're going to have to restrict the proof to a special case, and I think it's most unusual to find a student who can prove L'Hopital's rule, though most students tend to know it. Finally, Taylor series. My colleagues in the physics department are always saying this is the most important topic in calculus for applications to physics. And generally speaking, students can crank out Taylor series. Few of them can prove that a Taylor series converges, and fewer yet can prove that the Taylor series actually converges to the function. That's going to require Taylor's theorem with remainder, which we will do. So let's get started. First, inverse functions. I've got to remind you about a corollary of the intermediate value theorem. Suppose on some interval I, we have a function that's continuous and one-to-one. Let me see if I can use this to draw. Okay. Here is the graph of such a function. That's supposed to be a horizontal line. If the function's continuous and either strictly increasing or strictly decreasing, it crosses this horizontal line once and only once. So from the position of the horizontal line, we can get the point in the domain where the function crosses it. That's the inverse function. So the inverse function exists for a strictly increasing or strictly decreasing function. We've already shown that it's continuous, and this is a two-sided inverse function. That is, you compose f with f prime, or you compose f prime with f. In either case, you get the identity function. Now, I will admit that until I started teaching this course, I regarded the following as a valid proof. I said, f composed with f inverse applied to y is the identity function. Let's apply the chain rule. F prime evaluated at f inverse of y multiplied by the derivative of f inverse at y equals the derivative of y, which is 1, and as long as I'm not dividing by 0, it follows that the derivative of the inverse function f prime is 1 over f prime evaluated at f inverse. Example, f of x is the tangent function. The interval in question is the open interval from minus pi over 2 to pi over 2, on which the tangent function is strictly increasing. Then, the name we give to the inverse function is the arctan function, and its derivative by this formula is 1 over f prime, that is the derivative of the tangent function, evaluated at f inverse of y, arctan y. The derivative of the tangent function is the secant squared function. So we've got secant squared of arctan y, but secant squared is 1 plus tangent squared, so we've got 1 plus tangent squared of arctangent. Tangent of arctangent of y is y. We square it and get y squared. There's our differentiation rule, 1 over 1 plus y squared. Say, yeah, that's the proof. It's easy. Only one problem with that proof. I assume that f prime is a differentiable function. We have to prove that, and we will do it in class. Next topic, L'Hopital's rule. Now, there are many cases of L'Hopital's rule, and The way most students remember this is anytime you have a quotient of functions which is 0 over 0 or infinity over infinity, just keep differentiating numerator and denominator till you get something that makes sense, and that's the correct answer. It turns out that most of these different cases require subtly different proofs, so we're going to stick with just one case and prove it. Suppose we've got a situation where we have two functions, f and g, and as x approaches a from above, both of these approach a limit of 0. So the limit from above of f and the limit from above of g are both equal to 0. Then what L'Hopital's rule says is the limit of the ratio is the same as the limit of the derivatives. You can approach a from below, or you can have x approaches a from both sides, or you can have x approaches plus infinity or minus infinity. This result is still valid. It's even possible to have the limit of f and g be not 0, but infinite. But once you understand the proof in one case, you can figure out the proof in any of the other special cases. So we'll stick to one, and here's the basic strategy. Suppose we know that the limit of the ratio of the derivatives is L, then we can use the mean value theorem to construct an interval whose lower endpoint is A and whose upper endpoint is some alpha, and we can prove on that interval that the ratio of f to g differs from the quantity L by an amount that's less in absolute value than any pre-specified epsilon. That will complete the proof, and the trick is, as is often the case, use the mean value theorem. We'll do this in detail in class. Let's turn now to Taylor series. First, consider the simple case. Suppose we have a function that's defined by a convergent power series. In other words, for x less in absolute value than the radius of convergence of R, we define f of x as the sum of this convergent series. In that case, it's very easy to show that f of x can be written as the kth derivative evaluated at 0 divided by k factorial times x sub k. Why? Because this kth derivative over k factorial is just a sub k. But that's not the theorem we really want. We want to start with a function that's not defined by a power series. For example, the square root of 1 plus x, or the sine function, or the cosine function, and show that this formula is still valid. How are we going to do that? Well, let's start by thinking about the mean value theorem in the special case where we're considering the interval from 0 to x. Then the mean value theorem says that f of x minus f of 0 divided by x minus 0 is f prime of y for some y in the interval between 0 and x. I've taken the mean value theorem and multiplied both sides through by x. Now there's a reasonable looking generalization of this. Suppose I take f of x and subtract off not just f of 0, but f prime of 0 times x. And then I'll subtract off f double prime of 0 over 2 factorial times x squared. In fact, what I'll do is subtract off the first n terms in the Taylor expansion. What Taylor's theorem with remainder says is that the first term that I didn't subtract off is the remainder, everything that's left over, provided I evaluate the nth derivative not at 0, but at some point y in between 0 and x. In other words, there is some y for which this is an identity, and that's like the mean value theorem. F of x minus f of 0 is not f prime of 0 times x. That's the tangent line approximation. But if we replace the evaluation point 0 by some suitably chosen y, then we have equality. We're going to prove this by induction using the mean value theorem. The proof in Ross is one I've never seen before, and it's one of the nicest proofs in the entire course. Now, why is this theorem useful? Well, suppose we can show that for large n, the right-hand side here approaches the limit of 0. That would be the case, for example, if we can show that the nth derivative can never exceed 1 in absolute value. Then we've shown that if you take the function and subtract off the Taylor series, you get 0. The Taylor series not only converges, it converges to the function. The simple case, which I just mentioned, is all the derivatives. No matter how many times you differentiate, the derivative is bounded by some constant c. That will let you show that the Taylor series for the sine or cosine function converges to the function. And with a little extra effort, you can prove that the Taylor series for the exponential function converges to the exponential function. There's a second version of Taylor's theorem with remainder. The first time I taught this course, we proved that too, and I've now decided this is too much of a good thing, but I will state the second version. The fundamental theorem of calculus says we can get the difference between f of x and f of 0 by taking the derivative not evaluated at 0, but evaluated for all t in between 0 and x, and then integrating that. In other words, f of x minus f of 0 is the average value of the derivative on the interval from 0 to x times x. Let's generalize that. Let's take f of x and subtract off lots and lots of terms of the Taylor series. Then it's possible to prove that you can express that in terms of the nth derivative evaluated at points t in between 0 and x. You multiply by a suitable function and integrate. You can prove this one by induction too. You have to use integration by parts. There are a couple of cases where this version of Taylor's theorem with remainder is more useful than the first one. But for purposes of this course, I just want you to know that this exists. You don't even have to remember the formulation of it. Now, I keep saying the Taylor series converges to the function. How can the Taylor series converge to anything else? Well, here's the standard counterexample. I define my function f of x to be e to the minus 1 over x as long as x is positive. Now, this is a really weird function. As x approaches 0, 1 over x becomes larger and larger, but we're taking e to the minus that very large number. That's a very, very small quantity. So this function approaches 0 as x approaches 0 from above, and it does so incredibly fast. For 0 or negative x, this formula makes no sense. We'll define f of x to equal 0 for those values. It turns out that the Taylor series for this function is identically 0. Every term in the Taylor series works out to have a limit of 0 as x approaches 0. This function, however, is not the 0 function. So its Taylor series is the 0 function, but that is not equal to f of x. That's why we have to show that the Taylor series for a function not only converges, but converges to the function itself. Okay, so we got these 3 topics, and we're going to prove all the key results in class, in addition to doing some interesting applications of all 3 of them.